So thank you for the introduction, and also thank you to the organizers for the invitation. It's a lot of fun for me to see multidimensional getting used in new areas. Actually, there are some results I wasn't aware of. So, and I have to say, I really struggled because as I hear talks, I think, oh, well, it's really interesting to compare to this thing, but I don't just have time to put all that in. So I'm going to try and hopefully give a general overview. I am actually going to start from an atomic point of view. I know this is not an atomic physics audience, but for better or for worse, a lot of these techniques were developed by the AMO community. So a lot of the language comes from there and some of the insights. So I think it's actually useful to start from there and show you how it works in the systems. So by way of an outline, I want to start by introducing multidimensional techniques. Now I'm going to skip some things. Peter gave a good overview yesterday. So I'm going to try and build on that. And then, as I said, I want to show you some results in atomic vapor because it's a very simple system that even I, as an experimentalist, can do the calculations on the optical block equations to be able to compare. So I don't need any theory colleagues. And so that was actually part of the reason we did it in the beginning. However, it turns out there's some unexpected signals. Now, what do I mean by unexpected in this case? It's that they shouldn't be there in the single atom level system. So it turns out it's a signature interactions. And then I'll switch to probably what's most interesting, solids. I want to try to give you, convince you, and I think this audience, I don't need to convince very hard, that there are fundamental differences in the nonlinear response of a semiconductor compared to atoms or molecules, okay? This was something that was quite hard to sort of convince yourself of using traditional nonlinear spectroscopy, but the multidimensional spectra are so rich that I think it's quite clear. Also show that it is possible to look at effects of disorder and also get some insight into transport. And finish up, if you guys give me time, talk about some recent work on transition metal dipole-charged. All right, so Peter already stole my thunder about the fact that nonlinear optics was first discovered at the University of Michigan. Okay. With a second order response. But of course, we're always, for me, I'm always ignoring the second order response because it requires broken inversion symmetry. And I generally want a signal which will happen in any system. And also, I like signals that are about the same frequency as my incident electromagnetic fields, right? So since this requires broken inversion symmetry, I'm basically going to ignore it. We'll focus on the next term, the chi3 term. And the most generic thing we usually do is we illuminate the sample with 3 incident fields, okay? Here I'm being a little bit agnostic. This just says, okay, I have some phasor with a frequency, a wave vector, and this prefactor here has the amplitude in it and also has timing. So in other words, I would put t minus tau or something like that to time delay this. And in principle, this could be used for both frequency domain and time domain, but I typically always think about time domain, so I think of these pulses. And of course, I'm now going to a complex notation, so I have a C.C here. And so if I plug this into the third order 1, this looks pretty messy. I have all these terms, they're all multiplied out. So how do I actually simplify this? Well, first, I'm gonna make a couple assumptions. So first of all, I only want the terms that depend on all 3 pulses, okay? So in other words, a term like EA, that's third harmonic generation, but it's not particularly interesting. I would, just use a single pulse for that. And also where the polarization and thus the emitted radiation has approximately the same frequency as incident fields. So that means I need to pull a star out of one of these guys in order to do that. So these are the 3 remaining terms, okay? And these are typically, again, what you're in the terahertz regime, you often sort of can't do this separation that I'm going to talk about here. So you end up with all of these. And so it's a different question of how to separate them. One of the advantages we have in optics is we have good ways of being able to separate them. Means actually we can see quite weak signals. So I'll talk about 2 ways to do it. The first one is based on the wave vector. So if we simply come in with different wave vectors, again, in optics, these are going to be well defined. In terahertz, it's a little more tricky to do. But we come in with different wave vectors. And I should say, interestingly, of course, I don't know Peter actually said this, but of course, this was all based on multidimensional NMR spectroscopy, right? And of course, in their case, they have no hope of having a different wave vector because the sample is actually much smaller than a wavelength. And so again, they did things slightly differently that they connect as well. But so here I can just come in with different wave vectors, and then if you think about it, each of these terms will go in a different direction. Later, I'll show you where we actually use a different frequency, so each of these terms effectively have a different frequency. Okay.
Now, Steve, can I ask a question? How did you put a star on these? I mean, you just said let's drop a star. Yeah, what does that mean? I mean, I understand what that means, but how?
So the point is here, I've written now the electromagnetic field in complex notation. So I need the C dot C. Okay. So here I have a C dot C. So I was too lazy. I didn't write out all the conjugates. Okay. And so now I need to multiply all of these out.
Understood. So these were real things that they were already there.
They're already there. Yeah. They're already there. So all those are there. So this is a good question. So we always say, oh, one field's conjugated. Like, what do you mean? How do you conjugate? Oh, you mean you conjugate? No. So the point is, and so this is the other thing to understand, and this is actually where there's a big difference between optics and NMR, and somewhat of a difference between optics and terahertz, sort of in between, which is that in NMR they couldn't do this separation at all, right? Because they don't have different wave vectors, right? So they couldn't separate the linear response from the nonlinear response easily. And so in NMR, what they do is called phase cycling, okay? Again, they get these terms and then they systematically change the phases. And if you do it properly, then when you add, so they would do a 16-step phase cycle. And then if you add that up in the right way, everything would cancel except for this term, right? Now we're getting that for free here in the first by the wave vectors. And I'll show you later that what we do with this frequency shift is sort of morally equivalent to the phase cycling they do. What I've been intrigued in the terahertz is, and maybe this is because Thomas and Sasser did it first, is there's a tendency to do amplitude cycling, right? Where you do a different couple amplitudes and you add and subtract. I actually think that that's not the best way to do it, but I understand that technologically that's probably the best way to do it. So if somebody could come up with a way to do phase cycling in the terahertz, I think that actually could be an advantage.
Sorry, I have a stupid question. Terahertz, optical, visual electromagnetic waves. The issue is that the decays are too small to be useful, or
it's a question
in free space. There's still a
yeah, exactly. So that's why this is
I'm confused.
This is generic. You're right. No, the issue is simply so one question is simply the sample size versus the wavelength, right? So the point is, the sample size is small compared to the wavelength. You don't have well-defined K vectors.
That's fine.
That's it. Then so that's the fundamental difference, right? This is something that in optics, I'll show you at the end that we started to worry about. There's also just technological differences, and I'll point some of them out. I mean, again, in NMR, some of these things were trivial. That's why they did it in the 1970s, right? In optics, it's a lot harder, and I think terahertz, it's somewhere there's some things that are better in terahertz and some things that are worse. So, I mean,
but in principle, the real problem is only that I use a lens with an F number that is too large with terahertz. If I could just have optics where I put my terahertz on with a flat, then I could do all the
you could do that, but the issue then is you need a big sample.
That's right. So if I have an infinitely large sample,
you can
and I don't use an F number of 1, then I can do what I want.
If you have an infinitely large sample, in principle, you could do this in NMR as well, right? I mean, you can create a beam, an RF beam.
NMR, of course, but NMR is now extreme.
Yeah, that's extreme.
This is 300 microns at 1 terahertz.
Yeah, so really, it is sort of that practical issue of the wavelength versus the size of the sample. If you have a big enough sample, then yes, you can do it no matter what.
I can tell you later how we do phase cycling.
Okay.
Terahertz.
Okay. Yeah. I haven't read all the terahertz, but yeah.
No, that's okay.
Yeah. Okay. So now let me give you the way atomic physicists think of how these signals are produced. Okay. And so this is just for a 2-level system, an ensemble of 2-level systems in this sample here. Here I'll draw sort of what's happening in real space. This is sort of in a level scheme, and over here in time. So the first pulse comes in, and this is going to be in the language. Well, it could either be perturbation theory or sort of pi pulses, but I think mainly in the perturbation theory limit. So the first pulse comes in with a wave vector Ka. It puts the sample, the 2-level system, in a coherent superposition of the ground state and excited state. Of course, that oscillates as a function of time. So that means you have planes of well-defined phase. So the sample is going to remember the phase of the incident beam even after it's gone if the coherence time is long. You bring in a second pulse, and the second pulse will drive the system into the excited state, create a population wherever it's in phase with the coherence left behind by the first pulse. However, its antiphase will actually drive it back into the ground state. We generally, again, think of this as a population, so there's no evolution as a function of time. I just draw a constant line. Of course, that will exponentially decay. And then we come in with a third pulse. And what we think of is we think of it scattering off this grating that's been formed. So, right, so this fact that spatially there's a distinction between the excited state and the ground state means that now the transmission is spatially modulated, and so this pulse will diffract off of it. If you work it out, this grating has a wave vector of minus Ka plus Kb, as well as the opposite. It has both of them. But this signal we're going to pick out has basically the wave vector of the third pulse plus the wave vector of the grating. Right. Now, this is not new. So if we simply put a integrating detector here, and we measure the signal as the delay between Ka and Kb, so Ka will come first. In this sequence, we will get what's called a photon echo. So Peter pointed out when the first nonlinear optics was done. Does anybody know when and where the first photon echo experiment was done?
Schenck?
Not Schenck.
Okay, Groningen?
No,
Viersma?
before that.
Atomic vapors somewhere with nanosecond pulses?
Pierre Curie, not quite that old, just before the laser.
No.
So it was done not far from here at Columbia by Sven Hartmann in 1964, which again, I find amazing. 4 years after the laser was demonstrated, they did the first photon echo experiment. He came from the Hahn legacy, so that's why he thought, oh, let's try and take spin echoes and do it in an optical regime. Okay. It's pretty amazing because what he did, he had a ruby laser, and what he did to do this is he simply cryogenically cooled another ruby, so it became inhomogeneously broadened, and that was his sample. Everything was on nanosecond time scale, literally using an oscilloscope and a shutter in order to see, you literally see the pulses and the echo coming out afterwards. So the key thing about an echo, I'm not going to talk a lot about it, is the reason it was used for a long time by people like Schenck and Del Wiersma in molecules is the fact that you can overcome inhomogeneous broadening. So even if you're inhomogeneous broadening, because you're in this coherent superposition state in the first time, and actually there's a sign flip because of the fact that this guy is actually conjugated in this emitted field, it undoes the inhomogeneous broadening, and your exponential decay just measures the homogeneous line. However, there is a bunch of issues with the simple photon echo. Okay, so first of all, it turns out that if you do this in a homogeneously broadened system, that exponential decay goes at twice the dephasing rate. If you do a photon echo in inhomogeneous broadening, it goes at 4 times the homogeneous dephasing rate. Now, in one limit or the other, if you're very strong inhomogeneous broadening, you know how to interpret it, okay, and you're fine. But in the limit where they're actually similar, it actually can be ambiguous. I mean, so again, all you get is some decay rate from the photon echo. So to decide if it's homogeneous or inhomogeneous, you typically compare it to the linear absorption spectrum. Okay, and if you say that the line width I get is much narrower, that must be inhomogeneously broadened. But if they're comparable, it's actually because you don't know if you use the 2 or the 4. Okay, so that's one problem.
So Steve, can I ask another question? I mean, this tells you if I were just simply to do hole burning, would I get less information than this, or this is?
So hole burning is basically the CW equivalent to a photon echo. Yeah. So if you come in with a narrow band beam and you measure the absorption, that is for every one of these time domain things. There's usually a CW analog. Okay. So there's reasons why technically each one is advantaged. The problem with hole burning, so typically you'd use a CW laser, burn a hole, and sweep another one, right? The problem actually there is it's hard to have super broadband tuning CW lasers that tune nicely, whereas we know how to make super short pulses now, and so we can get a very broad spectrum. Okay. So another ambiguity of a photon echo is.
Yeah, I'm actually confused about that because if I look at your 3E combinations, they're all at different frequencies, whereas hole burning, there would be one place where I burn it and I need to, and that's a lifetime that would.
So they're all broadband. So remember there's that E out front. So the spectrum needs to be broad enough to cover the entire spectrum. So I have all the spectral information at once. Okay.
I guess I'm confused that if I do I don't do hole burning, but if I imagine doing hole burning and I see a lifetime to a hole, I can ascribe it to a lifetime of this particular part of the spectrum, those two level systems.
So in hole burning, that's not, so the equivalent to hole burning is not measuring the lifetime of the hole. So first of all, you can't measure the lifetime of a hole in a CW experiment, right? Because it's a CWB. You have to do something more. The point of a hole burning is you measure the width of the hole, and that width is the homogeneous width, okay? And so that's the analog. And so there, yes, you have one narrow and one broadband, okay? Or well, one tunable usually, right? So both CW. And so that's the analog. So you would have to do something. You'd have to actually go into the time domain to get a population decay by turning that field off. So the other ambiguity was actually sort of comes up with this is what happens if your homogeneous line width depends on position within the inhomogeneous distribution. This is something that people like Hartman and atomic physicists don't think about because usually that isn't the case. But in solids, and actually we saw an example from Oliver yesterday where that sort of naturally came out of the system. That happens in solids all the time. I see it a lot in terms of different sizes of nanoparticles, for example, give us different inhomogeneous broadening, but also different dephasing rates. And the final thing that turns out to be ambiguous, which was realized in the 90s, is if you see oscillations in this, that tells you have multiple resonances, but it turns out that if you simply measure the function delay, you cannot distinguish between what was called polarization interference, which you just have two independent systems, and the interference is purely electromagnetic, versus true quantum beats, which means that these are a coupled system, and you actually have oscillation in the quantum wave function. So these are the things that are limitations of photon echoes that motivate going on to do multidimensional. All right, so I'll give my version of how multidimensional works. Again, here is my pull sequence. I will label these. Here are my wave vectors. And down here, again, this is still just sort of the phasor of the incident field. The important thing is the signal has this, where it has a frequency that it emits at. So that's the oscillation as a function of this real time. And it has this initial phase, which is determined by the frequency that absorbed and the time delay between these two. And so we actually need to make measurements where this initial phase is preserved. Okay, that's actually a non-trivial task. But what we'll do then is we will correlate these two different frequencies at two different times by taking a two-dimensional Fourier transform. And when we do that, if it's a simple two-level system, we just see this peak here. And so let me now define my axes, which is that the Fourier transform with respect to tau is this vertical axis here. The Fourier transform with respect to little t is this horizontal axis. And note that because this guy is conjugated, there's a sign difference between these two. I choose to keep that sign difference and plot this guy as negative with its magnitude increasing down. So I'll typically put this dashed line on there. I've seen a couple conventions already in this conference. I'll say that in the broader, so the biggest community doing multidimensional is physical chemists. Some of them ignore this minus sign and just plot everything going up. Some of them keep the minus sign and still plot everything going up. Okay. There was and also some of them flip these two axes. I think I've seen that as well here. Actually, there's a conference called CMDS, Coherent Multidimensional Spectroscopy, and like 6 years ago, there was a survey saying we got to choose one convention. So they did a survey to see what most people wanted, and it was almost perfectly 50-50 split. So it's just like, okay, well, so you just always have to learn to look at people's plots and figure out what their convention is, and then do the weird rotations and flips in your head if need be. All right. So as we've discussed, inhomogeneous broadening causes diagonal elongation. Now you can actually measure the cross diagonal and the diagonal width. Okay, and we have a paper from 2013, I think, showing that you can actually, for a simple inhomogeneously broadened set of two-level systems, these are analytical, and you can actually fit them simultaneously to the same coordinates, and so you can unambiguously, no matter what the ratio is, pull it out. You can also measure at different slices, so you get these kind of pear-shaped spectra where you have different homogeneous widths at different places. So what does this require? It requires we measure the field, which in optics is actually not trivial. Of course, we naturally measure intensities. And it also requires precise stepping of the delay with interferometric precision. And again, these are most challenging in the optical regime. The shorter the wavelength, the harder they are. So we're going to have to go to, as I said, heterodyne detection. And we're going to have to go to a fair amount of work to make sure our steps are precise. And it's not just a matter, there's two issues with the steps. So one is if your time delay is jiggling as a function of time, that will blur out your peaks. But also if your steps are not precise, if they're really off, first of all, you get completely the wrong frequency, okay? But even if they're off by a little bit, I'll show you, we actually measure the phase, the real and the imaginary parts of the signal. And imagine you have a step error, which is roughly 1 over the number of steps. That's actually equivalent to flipping the phase all the way through 2 pi. And so that completely messes up the phase. So you have to actually be precise enough that you can preserve the phase over your entire scan if you're going to do that.
Excuse me, can I ask a question? If you, let's say that you are not able to have a local oscillator for one reason or another, can you frog the probe pulse and would you get the same information?
No, frog just, so key thing is, this is something that came up when I worked on combs and everybody, and there's this whole thing about the carrier phase and everybody does ultrafast says, oh, I can measure the phase, I do frog. Right? Frog does not care about the overall phase. And this phase right here that we need to get is this
absolute phase.
This is an absolute phase. It's not absolute phase of the laser. It's the absolute phase of the signal relative to the incident pulses. And the point is that absolute phase changes. So frog will not do it.
Thank you.
Okay. And actually, I'll just comment that if you look at some of the early theory, they actually didn't do it right because they failed. They just said the envelope was moving. They just put the tau, the delay in the envelope, and they didn't put it in the exponent. And that actually means the phase is not properly evolving. So you have to be careful about these things. Sorry, let me go back to here. So we actually use the so-called box. It used to be called the box-Cars geometry, where we have 4 pulses on 4 corners of a square. We have a 4th pulse that we use to actually pull out the phase delays and work as a reference. We then combine these and do what in ultrafast in this experiment is known as spectral interferometry, which is if you just have a known pulse and an unknown pulse with a known time delay, and you look at the power spectrum, you'll get fringes. And with a straightforward, it's not iterative, you just Fourier transform, filter, inverse Fourier transform. You can actually pull, and you do some division as well. You can pull out the complex spectrum with all the phase information of the unknown signal, as long as you know the reference pulse. It turns out that if you have something that's reasonably complicated, you don't actually know the reference pulse very, very well. As long as you know it's close to Fourier limited, it's fine. I'm going to skip this. It's non-trivial. We have Michelson and Michelson's with the CW laser actively locking in all this. Theorists don't care, and experimentalists get scared. So let me skip over that and get on to some data. So the first thing I'll show you, as I said, is a simple potassium vapor, right? So potassium is an alkaline metal. It has these famous D1 and D2 lines between the S1 half and the P1 half and P3 half states. These nicely work with our laser. And if we look at the simple linear absorption spectrum, we see 2 peaks, okay? And so this immediately brings up the question, okay, I know this is potassium, I know it's a D1 and D2 line, but let's say somebody gave me this sample and said, tell me something about it. I see these 2 peaks and I don't know if it's because I have 2 excited states or I simply have a mixture, right? It could be that I have potassium and something else in there, okay? So the linear spectrum is ambiguous. This red line for your information is just the laser spectrum showing that we're exciting both of them at the same time. So this is the 2D spectrum, right? Again, this is the Fourier transform with respect to the emission time. This is the Fourier transform with respect to the delay between the first 2 pulses. And what we see are diagonal features. The first one corresponds to both frequencies being the D1 line, and the second corresponds to both frequencies being the D2 line, okay? And what we see here are these off-diagonal peaks, okay? In NMR, these off-diagonal peaks won Richard Ernst the Nobel Prize in Chemistry, right? Because that's how you get structural information in multidimensional NMR from a molecule. But here they tell us that indeed these are a coupled system exactly as we expect. The cross peaks, so where do they come from in this picture? So one place they come from is simply that if we create a population, for example, to the S1, the P1 half state, that depletes the population in the ground state. So it modifies when we try to create this coherence to the P3 half states, right? So we call that ground state depletion. The other one is actually if we create a coherence between the S1 half and the P1 half, the second pulse can come in and create a coherence between the S1 half and the P3 halves. That's actually equivalent to a coherence between these 2 states. And then the third pulse converts it back to a coherence that emits here, okay? So this means we have a coherence between these 2 states, which in principle, there's no dipole moment between, all right? In the NMR language, they call that a zero quantum coherence because there's no quantum of electromagnetic field between those two things. And so this is actually pretty interesting because it means with this, we can start probing coherences which don't couple to the electromagnetic field. All right. As I mentioned, we can also get the real part of the spectrum. Again, I won't give you the experimental details. This is the experiment here, and we see this. This is actually like what I noticed Oliver showing yesterday, where we have this phase twist. This is just the so-called rephasing sequence. We have a positive peak in the diagonal and these negative wings. We have the appropriate ratio between these two based on spectral weighting and the dipole, and we see the cross-diagonal peaks are the geometric mean of these. This is our simple theory with optical block equations. It matches very well. So I do want you to take away from this, if you can remember in your head, the shape of these, that it's this positive peak on the diagonal, and the fact that this guy is the geometric mean of those two, which is exactly what you expect from a simple picture. Okay. Now we can do many different.
Sorry, Steve. These blobs, you also have a blob with the phases in your data, or do you get only?
This is with the phase. This is now the real part of the signal.
This is the real part.
Yeah. So notice that this scale.
But you could do an equivalent one with the imaginary. I mean, you know everything.
We know everything. So the imaginary is trivial. I mean, so it's just basically you when we do the extraction, you just shift by pi, and we can get the real and the imaginary part here. Okay. We typically just plot the real part. Okay. The imaginary part doesn't contain any new information. It's just a complex conjugate. Okay.
But you can imagine how when you're close to some resonances for some states, you do care about the complex multidimensional.
You can. And so what you care, you actually usually the C.C doesn't give you anything new. Okay. What you care about is the overall phase with respect to the incident pulses. Okay. And I'll show you that I will show you a case where this matters. That's why I want you to imprint on your mind what that line shape is. Okay.
If you care about line widths, then you do care about to be measuring, say, creating purely dissipative line shapes and this kind of thing. If you want to know lifetimes, right? Inverse lifetimes.
Well, you can get the line shape from just the amplitude as well. I mean, if you just take the amplitude, that's off its line width. You can get the line width from that as well. So the one advantage you have is actually if you do this so-called absorptive thing, where you add the rephasing and the non-rephasing, you actually get rid of those phase twist features, and then you actually get better resolution. So the line width you get depends on what domain you fit it in. Okay. It's generally is broader if you do it this or if you do the magnitude. And so if you have very close together peaks, then yes, it's best to actually do the real part.
Correspond to it. Maybe it's something I'd actually like to talk to you about because so it's something that we confront in the terahertz 2D spectrum where we want to get real widths of things. That it is this mixed line shape that has both dispersive and absorptive character. And if I just want to like fit a Lorentzian to it, then the data is noisy. So if it was a true Lorentzian, then it would fall off as R squared at high frequencies, and I would notice it. But the data, you can't really tell what power it's going at.
Yeah. So the thing to do is to do this absorb where you do real and imaginary, and so there's tricks to do that. The other thing is that whether it's a Lorentzian or square root of Lorentzian depends on whether or not it's homogeneous or inhomogeneous. So, and in principle, it's something between. It's actually a complex error function. And so you need to sort of take all that into account.
You heard this is what Oliver was confronting in his.
He was, and that's why I was asking him why he wasn't just doing what the physical chemistry community calls an absorptive spectrum, where he basically.
I think he was, but his phase up twisting, basically.
Well, I think he was doing something slightly different, which turns out to get rid of it in a different way. So
I think this is getting into a technical level.
yeah,
probably.
so, yeah.
Oh, yeah.
Okay. Okay. So
sorry, can I ask a question? I'm trying to make sense of your 4 blob figure. So the two diagonal blobs, just the 2 resonances, right?
yes.
And you had this totally different physical story of the lower of the bottom left and the top right blobs. So
totally different, but yes, it was.
So yeah, I guess why are they different? And why aren't they both just depletion features of the wrong?
So the fundamental, yeah. So the point is that the first order you just think, oh, it's a depletion. I've depleted one, and that's modifying the other one because I've depleted the ground state. So that's only one term. Okay. So there's another term where you create this coherence, where you excite one, you create a coherence between one, and then you create a coherence between the second one. And that's actually, if you do the density matrix, gives you a coherence between these two. Okay. And then I haven't talked about it yet, but we have that delay between the second and the third pulse,
Uh-huh.
and that coherence now exists in that time, and it will oscillate.
Okay.
And so if we did this, any one of these experiments, and we change that capital T, we call it, you would see that the off-diagonal peaks oscillate. Okay, and it's due to interference between those two terms.
So just to be clear, like, are both of those off-diagonal blobs, due to both those contributions, or is one of them?
Here they're due to both those.
Okay, good, thanks. That's what I was confused about.
However, okay, just to confuse, so if you do the non-rephasing sequence, it actually changes it. And so then those off-diagonal peaks become due to only one of them. I think it's actually the depletion one, whereas the zero quantum coherence rotates onto the diagonal. And some of those tricks is why some of these things work, where you add different ones and you reveal different things.
I have a question. When you say that these modes are coupled, what means that there is a kind of coupling parameter between them? Then we can imagine that we can, at least in theory, we can tune to zero, and that the intensity of the diagonal peaks goes down. What does it mean?
Yeah, hold on a minute. Okay. I know some of you don't like what you say, but hold on a minute. I'll come back to this. Okay, so we can do different types of multidimensional spectra. So this is the one I've been talking about. We call this, so again, we're Fourier transforming with respect to the first and the last delay, and the conjugated pulse is first. We call this a rephasing spectrum, because it undoes inhomogeneous broadening, just like the photon echo. We can do it where instead we scan the second and the third pulse. So this will get this coherence we were just talking about. It will actually extract that frequency. And so we actually call this a zero quantum spectrum. And we can also then switch the time ordering. So here Ka and Kb have switched. And we call this a non-rephasing spectrum. Some people, so Shel Mukamal, one of the leadist theorists, actually calls this S1 and S2 for various reasons. He labeled them that. I don't think that's very descriptive. And the last thing we can do is we can actually scan with respect to T and little t, but we move the conjugated pulse last. This is what we call a double quantum spectrum, and I'll explain why on the next view graph. So here's that sequence. The point is let's imagine we have a ladder system like this, where we have a ground state, a singly excited state, and a doubly excited state. We come in with our first pulse, we create a coherence between the ground state and the singly excited. The second one creates a coherence between the singly excited and the doubly excited. That's actually equivalent to a coherence between the ground state and the doubly excited. It actually evolves at twice the optical frequency. Again, there's no dipole, so it's not radiating second harmonic. You can't drive it directly, but that coherence is there. And so then we can read it out by coming in with another pulse that actually, again, drives between these two. We create a coherence here that radiates. We measure that. That's at the optical frequency. But the point is, if we now change the delay here, we'll actually read out the fact that this oscillation is at twice the optical frequency. Okay? So let's think about potassium. So in potassium, do we have a doubly excited state? We can get to the 5P and the 4D, but it turns out they're significantly detuned from twice the frequency of these. For the laser we use are outside the optical bandwidth. So we'd expect no signal, okay? No double quantum coherences, but when we do the experiment, we see them. Okay, so what's going on? So first of all, there's a hint here that this double frequency, again, since these now have the same sign, I'm plotting the double frequency positive and going up, is happening at twice the D1 frequency, the sum, and 2. So you say, well, wait a minute, maybe you can get this by somehow combining two atoms that each are oscillating at their fundamental frequency. And indeed, if you think about that, if we take two-level systems, you can do a Hilbert space transform where you create the outer product of the Hilbert space of those two. You get this. So this system, I call it a diamond system. You have a ground state, you have two singly excited states and a doubly excited state. If these guys are indistinguishable, then these become symmetric and anti-symmetric, and one of them is dark. If they're distinguishable, you still have two. But the point is, if you do your calculation on this, right, what happens is you see a signal. So I'm just going to talk about the double quantum, but it's more general. For example, if you go up here and create a coherence up here, you'll actually perfectly cancel with a coherence down here if the atoms don't care that the other one is excited. So if there's no interaction between them, right? If they do have an interaction, that can break that degeneracy, and now you get the signal. Okay, so this signal is due to interactions in some background free signature. To come back to the question you just asked, so the same exact reasoning works for the rephasing, right? And you find out that once you include this doubly excited state, that those off-diagonal peaks cancel perfectly if there's no interaction, okay? So this, you don't have to worry, this is even just at a two-level system point of view, right? So they cancel perfectly if there's no interaction and you don't see them, whereas as soon as you have an interaction, then they don't cancel and the off-diagonal peaks appear. So that's the way I think about it. Now, if you want to, again, I didn't put it in this talk, but if you think about a harmonic ladder, life becomes more complicated. But it turns out if you do have a perfect harmonic ladder, everything cancels. You get zero signal completely. So you need some anharmonicity, okay? But it turns out, so you will see a sort of the single quantum signal on the diagonal then. But in order to see the double quantum, you actually do still need interactions where there's a difference. The second excitation is more different than the first excitation. But it actually becomes really tricky because you get a lot of cancellations that are almost perfect. And so you have to be quite careful about it.
Reflect a different way. At the beginning, you were just making the sketch with the polarization as a chi-tree and then combination of the fields.
Yeah.
So the chi-tree itself comes from the anharmonicity of these levels.
So yeah, so if you want, yeah, so my point of view is a two-level system is as anharmonic as you can get, right? There is no, so a harmonic system, you're going to have multiply excited states, you can climb a ladder. If I simply say, okay, I move the doubly excited state completely away through some anharmonic coupling, then I can think of the two-level system. So yeah, does that make sense? Okay.
Over, but we had lots of questions.
Yeah, I want a chess clock here. So every time you guys ask questions, I can stop.
Exactly. But I think we should probably just go to the end of your time in this mode.
Okay.
So that's more profitable.
That's fine. You guys are more interested in the atomic part than this all. So we did some simulations with Shal Mokama. I won't get into details, but they reproduce it well, so it convinces this is right. Okay, so finally, let me get to semiconductors. So gallium arsenide is kind of the sodium atom of sort of optics in solid state systems. It's a simple system, couples nicely to light. So just to remind you, there's two valence bands, a light hole and a heavy hole, and then a conduction band. There's dipoles between these. It's 1/3 as strong for the light hole as the heavy hole. We're going to put these in a quantum well, aluminum gallium arsenide barriers. The quantum confinement breaks the degeneracy due to the difference in masses. So we now have two different transitions here that are distinct. And so we'll see two peaks here. Okay, so this kind of looks like a version of our potassium case where we see two peaks. And the question is, do we think of these as coupled or uncoupled? Okay. So this is the 2D spectrum. So up here is the linear absorption, the measured linear absorption spectrum. This is the laser. This is the rephasing and non-rephasing. We look at this. Okay, so there's a bunch of surprises. Now, first, I do need to say that this is with co-circular polarized excitation pulses. So the first surprise is simply the presence of cross peaks. So why is that a surprise? Well, this is the magnetic substates. So we -3/2, +3/2, -1/2, -1/2. So co-circular. This looks like two uncoupled transitions. So you would expect no cross peaks from that simple picture. The other thing is not only that, look at the cross peak, it's the strongest feature. Now remember, I asked you in the potassium case to remember that the cross peak was the geometric mean of the two diagonal peaks. So here, it's not the geometric mean. Not only is it not the geometric mean, it's actually stronger than the diagonal peaks. The second thing is the line shape. Okay, so here we see on this line clearly what looks like so-called dispersive. So as a matter of fact, when I first showed this to my physical chemistry colleagues, I said, you don't know how to get the phase. This is the imaginary part, not the real part, because that's what you expect. So that's actually part of the reason we did the potassium, was to convince them, yes, we do know how to get the phase. This is physics. This is that there's a different phase of the signal compared to the incident pulses as compared to a simple atomic system. The other thing is this vertical stripe, right? So this vertical stripe is the continuum, all right? There's certain famous people like Chuck Shank who said, oh, the continuum is a photon echo, and so that should be over here diagonal on the diagonal, but it's not, all right? I can give you in these papers sort of phenomenological explanations, but we recruited some theory help from Peter Thomas and Torsten Meyer in Marburg. And so they did theory. So they take a one-dimensional chain. They have the heavy hole, light hole structure in each element of the chain. They turn on coupling, get the effect of mass. They turn on the Coulomb interaction, get exciton binding. And the only thing they adjust in this is the dipoles to match the linear absorption spectrum. They need to do that because it's one-dimensional, not full two-dimensional. And the only thing adjusted to match the 2D spectrum is the dephasing rate, because you can't get that uniquely from a linear spectrum. To me, this is important because if you let a theorist adjust everything to match your 2D spectrum, I'm sure that they can match any theory to your spectrum. The key thing is we're saying do it to the linear spectrum, get that right, and then minimize what we adjust. So it's not going to be quantitative because it's discrete in 1D, but you'll see it gives good insight. So again, here's the experiment. And here is the first level of theory. So they call this a polyblocking level. So what they've done is they've kept the Coulomb interactions, so you get excitons forming, okay? But then they've ignored all interactions, which are due to things like dipole-dipole interactions by excitonic effects. And what you see is actually this looks kind of like what you might expect from potassium. This line shape is clearly sort of just has these phase twist wings. You don't see much of a diagonal peak. So clearly this is not matching very well to this. So the next level is they keep the interactions between the excitons, but they truncate the hierarchy of equations based on the Coulomb interaction. So it's sort of Hartree-Fock or a mean field theory. They only take the first order. And you see improvement. The line shape is getting better. This is getting stronger, although it's not the strongest. The continuum, I should have said, is on the diagonal over here. Now it's sort of, you're seeing interactions. It's discrete because of the finite size, but you see sort of a grid here. The last level they call a full calculation, or it's better called dynamics controlled truncation. And with apologies to the condensed matter theorists in the room, I call it sometimes condensed matter theorists learning to do nonlinear optics. Because what it entails is basically truncating the hierarchy, not on the Coulomb interaction, but on being in third order in a laser field, okay? So you need correlation terms beyond a mean field, okay? They start to capture some of these interactions and you see much better agreement. You now see that this is the strongest one. You see these vertical stripes and the line shapes match well. So the message is that only this full theory reproduces the experiment. And the theorists have told us for quite a while that these terms, these correlation terms, were strong. Okay, so they're important. But I'm like, I'm sorry, I don't have a switch on my cryostat that says turn off correlation terms. So I can't do that comparison that they can, right? And if you do a 1D experiment, you see a curve with some wiggles and a decay. And you could actually fit that with like a very simple optical block model equation with some corrections, okay? The point here is that these 2D spectra are so rich, there's so many features that I think that even if you took somebody who didn't know any physics and said, which one of these matches this better, I think they would pick out that last one and say that theory matches better. So it's the richness that really matters. I like to say this way, in my simple way of thinking about it. So the point is that the optical response of semiconductors is very different from atoms or molecules, okay? In atoms or molecules, it's due to polyblocking, the fact that if you put one electron in a state, you can't put another one there. Okay, whereas in semiconductors, it's a many-body effect. And so I love this diagram from the Tuke. And so my point is that in semiconductors, it's actually the cloud of dust that's giving all the response. In other words, you know, the nonlinear response could be the horses colliding with each other, but it's actually because the horses slow down when they go through the cloud of dust of another horse. It's just that the cloud of dust is so big, it's what's important. So, okay, I think I'm at the end. Let me just say one more thing here. So this is double quantum on quantum wells. And so the point is we can do different polarization. So this is where we actually should be able to go to this biexcitonic state. If we change the polarization, we can't go to the biexcitonic state. There's no state there. We still see a signal. Again, this is because we have interactions, just as it was in the potassium paper. This peak here is actually the biexcitonic peak. This is also due to interactions. Again, Sean Mukopal's group did theory calculations that match quite well. But an interesting thing from a theoretical point of view is what they realized is that this unbound 2-exciton peak here, which we see here, is actually a mean field term, okay? So it doesn't need those higher order correlations. And so what's interesting now is by comparing these different spectra, maybe you have a way of actually teasing out the different terms in your nonlinear response that are mean field and the higher order correlation. So, all right, I think I'm at the end of my time. I already had a lot of questions. I have a lot more I could talk about, but maybe we'll stop there. I can talk about transport, localization of delocalized states due to disorder in quantum wells. We also, I'll skip over this quickly. This also might be interesting that Martin Richter at TU Berlin realized that you could take actually de-blurring algorithms and basically apply them to these spectra. So if you have a theory friend who doesn't want to learn about nonlinear spectroscopy, but for example, can do transport calculations, oops, sorry, you can actually take the data. This line shape function is equivalent to the point spread function that you use in this de-blurring algorithm. And then you can actually extract out basically the Green's functions of the transport. So this is transport due to motion between localized states. And then we have this other method where we use frequency shifting. I won't go, the important thing is that now the pulses are all collinear. So we can focus down very tightly. We can look at small samples such as TMDs. We can see that they are actually still inhomogeneously broadened. Also, they're quite, so we can figure out what the mechanism is, but we can also image. So we can, so that like this is an example where you get quite different, same sample, two different locations. This is obviously clearly inhomogeneously broadened. This is closer to homogeneous. You might not be surprised. You can see there's maybe a wrinkle in this sample right there that's doing this. So it's important to actually image, and we've shown you can image. The imaging actually can tell you about how many layers there are. And you can look at kind of correlations, and we can actually, at each pixel, we can actually get the homogeneous and inhomogeneous line width by doing this rapidly. So let me see, let me just, I'll skip to. Let me just, I have a summary, but I didn't have everything. So these are all the people, people at Michigan. A bunch of these people have left already. Postdocs that have moved on. I started this at Gilla with a lot of collaborators. And as I said, if you want to learn more, we recently published this book. So with that, thank you for your attention.